Yeah, and for the last two lecture video of ours, I think there was a problem of the voice not being recorded. So yeah, it's a new MacBook that I started to use, and the setting was a little bit, setting was wrong. So it's now recording our voice as seen here. Okay, so last time we studied about this variable selection method of a forward stepwise and a backward stepwise manner. And then in general, if we include more and more number of variables, whether it is a forward or the backward stepwise selection, I mean more variables, and then the training error will be will be smaller with the more number of variables. So in this case, we considered about the risk of being overfitting. And so considering such an overfitting due to like complicatedness of our models, there were several different measures that penalizes those models with the more variables corresponding to more number of parameters to estimate. Okay, so by using them, we can find out the optimal subset of our variables to use for our regression, and also empirically, even without considering these complicated measures or non-intuitive measures, we can just utilize our validation set and their performance or loss to determine which particular subset of the variables will be our optimal set for our model. So that's how we perform our model selection, including this number of variables to include, and also the step size and some other hyperparameters as well. Okay, so that was the about the variable selection. But in practice, in the era of deep learning, I personally see the main one of the main distinction between the machine learning and also deep learning versus like the traditional statistics. So in the case of statistics, they really focus on selecting highly curated variables that fits their own assumptions, and so they really put a lot of an efforts to find out this optimal set of a subset of our variables that we are given initially. But in the case of machine learning, whether these variables are helpful or not for our own prediction task, we just dump them into part of our input feature vector. So as long as we provide a sufficient amount of data, and then our model will be intelligent enough or smart enough to filter out. 네, 이 모니터가 안 켜져서 이게 안 나오나요? 이 모니터 키니까 이게 또 나오네요. 모니터. 어제가 됩니다. 일단. 오래 걸리는. 키는데 좀 시간이 걸리셨나요?
아니요, 근데 새로 킬 때는 빨리 됐거든요. 그 전에는 한참 기다려도 안 됐고, 지금 사실 모르겠어요. 뺐다 꼈다가
여러 번 했는데.
근데
이 컴퓨터가 켜져야 뭐 저기 좀 켜지고 그러는 게 있나요? 지금? 그건 아니에요.
그 원인을
하여튼 뭐 일단 됩니다. 네. 다음에 될지 모르지만. So in the case of machine learning and deep learning, we don't care too much about selecting the helpful variables. So these kind of variable selection is not widely used in practice in these days. Especially when using deep learning and advanced machine learning methods, such as decision trees and gradient boosting trees and so on. Okay, let's move to the shrinkage method. This shrinkage method is a kind of soft selection of variables. I mean, the approaches of selecting softly our variables. And so, if you're familiar with the L1 or L2 regularization, these are the methods that we discussed over here. Okay, so we have a main loss from training data fitting, and then we have some regularization. Okay. So I'm gonna skip this. I'm gonna skip the detailed explanation about this because most of you guys would be familiar with these. Right, and yeah, these are called the shrinkage method, and yeah, this is one example of applying the shrinkage method, especially for L2 regularization. So when using the linear regression with the L2 regularization on our coefficients, that is called a ridge regression. Okay. So in this case, x-axis is our hyperparameters that assigns particular weights to this regularization term. So yeah, as we can see, with a larger value of lambda, then we impose the stronger regularization. So all the coefficients, so each of the line is the coefficient, I mean learned coefficient for each variable. So if we have 1, 2, 3, 4, and then maybe some other variables as well, and then in this case we have approximately 10 different variables as an independent variable for our linear regression. And then this part is the fitted result or converged parameter values when we fix or when we set our hyperparameters for for this regularization term as this value. Okay, and then if we use the stronger or larger values, and then more and more coefficients will be suppressed towards 0, right? So it's interesting to see not all of them is monotonically decreasing towards 0. So some variables are actually increasing in terms of their coefficient. And then there could be many many possible scenarios that made it possible, but so yeah, if we start to suppress stronger, and then the model may just rely on this variable heavily. I mean, in this case, suppose maybe this guy and this guy is starting to shrink towards 0 around this point, right? And then in this case, suppose this blue variable is highly correlated with the other two, red and black. Okay, so in this case, it didn't need much of a coefficient, right? But when these two starts to shrink towards 0, and then so you can roughly think of it as when excluding these two variables, and then I mean our alternative strategy would be to use the single variable that can kind of replace both of these two. And so if our shrinkage is too strong, and then we can just suppress the two other variables and then just rely on a single variable that can reflects both of these two variables. Okay, so that's just a conceptual and a hypothetical kind of explanation, but you can kind of get some understanding or intuition about whether this is possible or not. Okay, and also sometimes in some of the variables it was a negative it was assigned a negative weights overall, right? But when other variables are suppressed strongly, and then it has to get assigned a positive coefficient as well. So this kind of pattern is quite random. But anyways, this is one example of ridge regression and their patterns of the shrinkages of this coefficient corresponding to each variable. Okay, and then yeah, how do we select this hyperparameter assigned to the assigned as a weight to this shrinkage term or the regularization term? So yeah, we also have to do the same model selection based on either validation data and yeah, some of these measures, like I don't know which, but let's see. Yeah, this kind of measures. Yeah, as I mentioned, these are giving some penalty term or quantitative penalty for complicated models, right? So in this case, if we use a stronger regularization parameters for regularization terms, and then this guy can give a smaller penalty because that is considered as a simpler model compared to the case where we used a smaller hyperparameters over here. Okay, so we can also use those specialized measures, but in practice, I think we just mainly use this validation loss to determine the optimal hyperparameters. Okay, then okay, so yeah, let's imagine the optimization, or yeah, how to obtain the optimal parameters for our beta to minimize this regularized version of linear regression loss. So in this case, yeah, the first strategy would be to apply the gradient descent, right? So gradient comes from this term of a fitting loss of a training data, and also the gradient comes from over here, right? So from these two terms, we will receive the gradient for each variable, and thus they will work as a driving factor to update our parameters. But if you guys remember, there was a closed form solution of our linear system, least squares, right? So given ax minus b, so this is a least squares problem, right? So this x is our vector composed of the beta, right? So I think we briefly looked at this slide. Then there's okay. Let's see. Okay, so we looked at this example, right? And so from here, we have x1, x2, and x3. So these are coefficients assigned to each variable that we have. And so in this case, we just represent this problem in this form. So v over here, which is the high dimensional vector, where the dimensions, the number of dimensions is the number of data items that we collected, right? So for example, here we collected 4 data items, 4 people's record of input variable height, weight, height, and is smoking, and then his or her lifespan as our ground truth data, right? So this is our B, and this is our entire coefficient matrix A, and then x1, x2, x3 are the linear combination coefficient for our least squares problem, right? Right, and then A times x will give us our predicted result for his or her lifespan, and then these are ground truth values, and so we just take this subtraction between them, and then we minimize the total loss between of these, so squared sum of these, right? Okay, so that was the problem setting of our least squares. Then what was our solution? I mean the closed form solution. Closed form solution was A transpose A x is equal to A transpose B, right? And then x is represented as A transpose A inverse A transpose B, right? So that is our closed form solution for linear least squares, right? Okay, so back to our problem of regularized version of least squares. Okay, so in this case, yeah, we can of course apply the gradient descent as we discussed already. But furthermore, we can obtain the closed form solution for this L2 regularized version of the least squares. Okay, so that is represented as follows. So I'm gonna just give you the answer. So that is A transpose A plus lambda I inverse A transpose B. Okay. So so this is our objective function. So like this guy plus lambda this guy, right? So does it make sense? So these two are the same one, except for the notation difference. So instead of beta, I just use an x, right? Okay, so I just mentioned that we have a closed form solution for this regularized version of least square problem as A transpose A plus lambda I inverse and A transpose B, right? Right. So let's derive or prove that this guy is a closed form solution for this optimization problem. So this is a little bit of a linear algebraic tricks. Okay, so in this case, we can rewrite this regularization term in this manner. Does it make sense? So for example, let's see. So suppose A is 5 by 3. So we have a 3 variables but 5 equations. Okay. And then here we have 2, 3, 4, 5-dimensional vector B, right? Right. So and then this guy, I'm gonna write it into identity matrix. What is the size of an identity matrix? It's of course 3 by 3, right? x1, x2, x3, 1, 1, 1, right? And then what is this 0 vector? So that is of course 0, 0, 0, 3-dimensional 0. Right? Okay, so here we can interestingly rewrite this equation into this single 2 norm squared, and so this is our A, right? So this is our I, and let me just first put it into the squared form, and then it will be lambda squared. Does it make sense? So lambda times the 2 norm of some vector, and then sorry, it should be square root of lambda, right? So if we just put it inside of our 2 norm, and then you can see that square root of lambda times x1, square root of lambda times x2, and so on, and its 2 norm will be lambda times x1 squared plus lambda times x2 squared, and so on, right? So we properly put the lambda into the 2 norm, okay? And then now I'm gonna give you the new expression for this guy as, so we have a over here, so it can be represented as lambda I. So 1 2 3 4 1 2, so it's still this 5 by 3 matrix, and then we have this lambda square root lambda I, right? And then we put that square matrix over here, lambda I, okay? And then we still put the x over here, x1 x2 x3, and then we have b here, or b, and what, 0. Right? Can you see the equivalence between them? So yeah, we can see that this guy is the sum of squared elements, element-wise squared sum, right? So as I said, yeah, this guy is like square root lambda x1, square root lambda x2, square root lambda x3, right? And then what is the 2 norm? It's just a squared sum of them, right? And then what about the 2 norm over here? It is like this guy times this minus this guy squared, right? And this guy times this minus this guy squared. So they are just a squared sum, right? So each row over here, each row is decomposed into the sum of the squared version, right? Okay, then let's consider this case, okay? So now the vector to consider to compute the 2 norm is having more dimensions. So here we have 5-dimensional vector and its 2 norm, and 3-dimensional vector and its 2 norm, and it's now 8-dimensional vector and its 2 norm, right? But still, if you imagine how we compute the 2 norm of this entire expression, what is the first dimension? Was the first dimensional entry? So this guy times this minus this guy, right? This guy times this minus this guy, right? And so they will be just a summation between this upper part and the lower part, right? And then they will be added together, and then we see addition over here, right? So in this case, let's rewrite its closed form solution by just looking at it as a single standard least squares problem. So now this part is new a prime, right? And then we know the closed form solution, or its normal equation is a plus lambda I transpose a plus lambda I. So that is corresponding to a prime transpose a, right? And then its inverse, and then what is our a? A is lambda I, right? So that is a prime transpose, and b. What is b? B is we have b over here, and 0 vector over here, because that is our new V, right? So far so good, right? Okay, and then let's evaluate this expression inside of our inverse operator. A transpose A, right? And then what about this part? Lambda times I transpose A. I transpose is just an I, so is A. So something's wrong. Lambda and A and is it A transpose? So A transpose and this guy is corresponding to this guy. Where is wrong? What is wrong here?
I 앞에 루트 안 닿았어야 되는 것 같고
루트요? 네.
A랑 I랑 사이즈가 다른데 어떻게
네. 그렇죠.
잘못했지?
잘못 썼어요 완전히. 여기가 이제 so the addition is wrong, right? So we just think of this concatenated version columnized between A and lambda I, but it is not a plus lambda I, right? But when computing this concatenated version, and then we will obtain this summation kind of form, and so I wrote it too early, and it is clearly wrong. I want to go back. Okay, might have been faster if I used the eraser. Okay, hey, and lambda I over here, right? So this is called a partitioned matrix, okay? So this is called a partitioned matrix. So it is just this guy, A and lambda I, and their concatenated version columnized, right? And then, so we consider it's a transpose first, right? Because A transpose and A and inverse is what we need, right? And so if we transpose it, and then what will be this result? And then it will be A transpose and lambda I. Does it make sense? So it is transpose result of this partitioned matrix. Okay, so so we have to use its inverse. Sorry, this should be inverse. Sorry, should be inverse, and then A transpose is this guy, right? A transpose and square root lambda I, and our vector B, right? So B over here and 0 over here, right? Right, then what is this result? So if you are familiar with this partitioned matrix and their multiplications, this case, you can just think of it as the inner product between these two. So that is the multiplication between the partitioned matrices. Okay, so in this case, I transpose A plus lambda I times A plus A transpose. Sorry, what am I doing? I squared and lambda, right? Okay, so inverse. And then what about this result? So we still perform the inner product between the two, right? And so what is that? A transpose B plus, what about the multiplication between the second elements? It will be 0, right? And so we just have 0, right? So we transpose A plus lambda I and a transpose B. Okay, so what we did was to obtain the closed form solution of this Ricci regression or L2 regularized version of the least squares. Okay, as I mentioned, yeah, so this one is our result. Any questions? And yeah, regarding this partitioned matrix and their multiplications, yeah, if you play with, if you're very good at manipulating these kind of setups or settings, and then it will be really useful tool for your own research when you use some linear algebraic techniques. Then let me give some more examples. Yeah, so yeah, from here, yeah, so from here. So A was originally 5 by 3, right? Although it is a really small one, but 5 by 3 transpose is 3 by 5. 1, 2, 3, 4, right? And then for lambda I, square root lambda I, and then it is just a like this guy, right? So yeah, I'm just showing the actual multiplication. So this one is a transpose. This guy is our lambda I, right? And then A is also okay, so we have this part of an A, and it is no longer, it doesn't look like a square matrix, but this one is lambda I, right? Right, and so okay, so what is A transpose A? And let's consider the size of it. Okay, size of it, and then the size will be just a 3 by 3, right? And then what about the first element? I mean, I'm gonna just give you the example of computing the first element. The first element is computed by the inner product between these two vectors, right? And then from here, we first compute the inner product up to 5-dimensional vectors, right? That will form the first element of this guy, right? And then also this part, okay? This part will form the first element of lambda I squared, right? Okay, so we are adding together, right? So that way we can easily see that this guy, at least for the first element, we can understand that this representation is the same as like given these two big matrix and then performing the single inner product. Okay, so these two are equivalent. So writing in this form is indeed true. Okay, so we at least verified they are true for 1, 1 element. And then similarly, we can perform this kind of partitioned matrix and their product in the form of an inner product form. Outer product form, or even like this form. Okay, so let's call this part as A, B, C, D, E, F. So for example, A is maybe 3 by 4, and maybe 2 by 3, and 2 by, yep, 2 by 4, and maybe 2 by 2. I mean, I'm just giving you some example. And the E is 4 by 3, for example, and it is 2 by 3. Okay, so that's how we match the size, right? So in this case, when multiplying these two partitioned matrices, and then the result will be just like the result when treating A, B, C, D, E, F as a scalar. Okay, so in that case, AE plus BF and CE plus DF, something like this. Okay. Okay, at least let's check the size. A is 3 by 4, and E is E is 4 by 3, right? 4 by 3. Okay, and so it is giving us 3 by 3, and BF is 3 by 2, and F is 2 by 3, right? So we cancel these two out, and then 3 by 3 is obtained. So at least the addition between the two are valid. And then this part is the upper part, where we just compute the inner product of like this guy to obtain this, and this guy is obtaining this, and so on, and then this guy times this, and so on. So we will obtain the second row, and then we have 3 rows, and then we obtain the 3 row. Okay, so that way the first 3 rows are only involving A and B part, or the upper part of the left matrix. Okay, and then similarly we can define this outer product as well. So I made it dramatically different. AB let's see. CT. Is it possible to define? Yeah, it is defined, I think. So it's too long. So okay, so AC and AD and BC, BD. Okay, so this kind of a outer product perspective of this partitioned matrix will also hold true. So it's like, so suppose this size is 3, and then maybe 4 and 2, and then maybe 5 and 6. Okay, so let's at least verify the size. What is the size of AC? 4 by 3 and 3 by 5. Okay, so 4 by 5. Okay, and then what about the AD part? Yeah, we can see that 4 by 6. And this part, BC, is 2 by 5, and this guy is 2 by 6. Okay, so checking these sizes is at least giving us the valid matrix partitioning. So for example, suppose this is a 4 by 5, so it has at least 5 columns. So does this lower part also have a 5 column? Yes, it is, right? And also we have 6 columns over here, right? And also between these two we have 4 rows and 4 rows, right? So this partitioning is a valid shape of these 4 sub-rectangles to form the single large rectangle. Okay. So it may look a little bit boring, and you may not understand why it is needed, but yeah, this kind of thing is really high level and I would say really beautiful kind of manipulation techniques of the linear algebra when dealing with those techniques in your own research. Okay. Any questions? 네.
솔루션이 그러면은 A 트랜스포즈 A에다가
네.
거기 뒤에 이제 람다의 아이덴티티 매트릭스가 추가로 더해지는 거잖아요.
네.
그러면 두 개 이제 컴퓨테이셔널리 익스펜시브가 더 추가된 건가요? 그 계산을 해야 하는 거거든요.
일단 이 클로즈 폼 솔루션 측면에서는 컴퓨테이셔널 인텐시브한 거는 별로 없는 것 같아요. 왜냐하면 그냥 A 트랜스포즈 A에다가 이제 람다 I라는 건 이제 대각선에다가 람다들을 쭈르륵 더해주면 되는 거잖아요. 그렇기 때문에 이제 그러니까 뭐 이게 계산상으로는 그렇게 어려운 일은 아니고, 그 다음에 결국은 뭐 이거 다음에 뭐 인버스를 구하든 아니면 이거를 뭐 리니어 시스템을 통해서 풀든 어쨌건 뭐 조금 더 변형된 매트릭스에서의 어떤 그 노멀 이퀘이션을 푸는 거라고 생각을 하면 되니까, 뭐 어떤 지금 뭐 우리가 다뤄야 되는 매트릭스 사이즈가 커졌거나 그런 건 전혀 아니에요. A 트랜스포즈 A라는 매트릭스 여기서 그러니까 뭐 방정식이 5개, 미지수가 3개였으면 일단은 노멀 이퀘이션에서 풀어야 되는 이 A 트랜스포즈 A라는 매트릭스는 이제 3x3 매트릭스로 나오고, 이 3x3 매트릭스에다가 이제 대각선에다가 이제 람다만큼만 더해주는 거거든요. 네, 그렇기 때문에 뭐 계산상으로는 아마 최소한 이 노멀 이퀘이션 측면에서 어려워지는 거는 거의 없어요. 네. And also, yeah, from the linear algebraic perspective, adding this lambda I has some interesting kind of effect. So let's imagine some extreme case where lambda is kind of positive infinity. Okay, so suppose A transpose A is something like 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is just a random matrix, and then we add some lambda over here, and then suppose lambda was 1,000. Okay, 1,000. Okay, and in that case, if you guys remember some condition number or the stability of our solution, so in this case, so our normal equation is like given this matrix A transpose A and X, okay, X1, X2, X3 is A transpose B, right? So in this case, I mentioned that like those 3 vectors will work as our some basis, right, to fit this guy. And if you remember some parallelogram that I mentioned, there should be some parallelogram that I drew. 어디 있었는데? 또 작은 데다가 이 코딱지만 하나 그렸나? Okay, so I'll just simply briefly redraw it. Right. So in the case of a highly correlated input variable, so you can see that height and weight are already non-trivially correlated with each other, right? So in that case, it leads to highly similar vectors in our A transpose A. So in this case, if it is a 1, 4, 7, indicating a particular direction, and then the second vector is having almost the same direction, okay? And then let's remove the third one, And then in this case, yeah, so as I drew last time, we are given some vector A transpose B, and then suppose we have really narrow angled two vectors, and then like this guy, this guy, okay, something like this. Okay, so it's very narrow, and so if we involve some numerical errors when representing these two vectors and their elements, and then if we have a slightly different or wrong angles, and then their linear combination coefficients corresponding to the scaling factor of this guy, and this part. Okay, so this linear combination coefficient that works as a scaling factor of our original input vector to fit this force, this given point of an A transpose B as force point in our parallelogram. Okay, so if we have a really narrow angle, and then we may get a really unstable solution, right? So in this case, why do they have similar angle? Okay, so what's the meaning of having the similar angles for the two vectors? So suppose it's a little bit 45-degree angle. So I'm gonna give you a new example of maybe the first vector is 5,1. Okay, what's the meaning of having another vector with the really small angle with this guy? Okay, so that guy will also be like 5.1 and 0.8, for example. So in this case, it will be something like this, right? So this is the case, right? So in this case, 5.1 and 0.8 and 5 and 1. So this will be our kind of two basis vector that have really small angle, right? But in this case, I mean, even though I didn't show it rigorously, but if your variables are highly correlated, okay, and then the columns of A transpose A will have really minimal angle or small angle. Okay, small angle meaning we have this kind of pattern, right? So if we have a large element, and then also the second vector will also have a large element. So that's how we obtain the small angle, right? So in this case, if we add our regularization term, what's the effect? So like 1,000, things like that, right? So in this case, right, the first vector have been, the first element was added with the 1,000, right? So it will be more towards the first axis, right? So this point will be somewhere around here, I think, right? And then what about the second one? Okay, so second one initially had a similar angle of having a large value in the first element and then the small value in the second element, right? But we add large value in the second element, and so this guy is actually moved towards, close to the second axis, right? Okay, so if we generalize or extend it to a higher dimensional case, okay, and then suppose in the three-dimensional case, suppose the three of them, because our variables are highly correlated, and so they were pointing out really similar kind of directions to the similar directions. But once we do the unregularization, the first axis, the first variable or first column will be really put or placed close to the first axis and the second axis and the third axis, and so we almost get orthogonal bases, right? So that way our solution becomes much more stable. Okay. So this kind of regularization stuff is quite useful for making really stable bases, meaning that they have maximum possible angles for any pairs of the vectors, right? So if we consider those column vectors that are just attached or just put exactly onto each different axis, and then any pair between the two, I mean any pair of the two basis vectors will have the maximum degree of 90 degree, right? So from the numerical stability perspective, this regularization is giving us like robust solution, or it makes our solution more robust against this highly correlated input variables. Any questions? 네.
근데 A 트랜스포즈 A는 시메트릭 매트릭스인데 방금 같은 매트릭스 아닌지.
좋은 지적이네요. 근데 뭐 발생하려면 하겠죠? 보자. 그러게요. 그러면 얘가 크고 얘도 크고 또 얘도 크고 얘는 작고 근데 얘는 얘여야 되니까 얘도 크고 얘는 얘여야 되니까 이렇게 되고 또 이거 됐어 보자. 여기가 100이 됐으면 얘네들도 100이 돼야 되고 같은 방향이고 또 얘도 또 100이 돼야 되고 얘도 또 100이 돼야 되네. 네, 그럼 결국은 이거는 45도로 다 모인다는 뜻이네요. 그러니까 일단 내가 얘기한 게 아마 틀리진 않았을 거고요. 틀리진 않았을 거고 아까 이제 이야기했던 것을 여기 대입을 해보면 여기 적용을 해보면 같은 앵글이 돼. 그 A 트랜스포즈 A가 거기서 나타나는 컬럼 벡터가 이제 그 같은 방향으로 나타내려면 그거는 일단은 그 45도 방향, 그러니까 하이디멘셔널 스페이스에서 45도 방향이라는 게 좀 애매하긴 하지만 어쨌건 이제 1,1,1 혹은 1,1,1,1 뭐 이런 벡터를 45도 디렉셔널 벡터라 그러면 그쪽으로 다 모인다는 좀 뜻이 되는 것 같은데요. 그러면 이게 좀 이것도 한번 좀 따져보죠. 정녕 그런가? Right, so let's think of two exactly correlated variable with the correlation coefficient as a 1. So maybe 147 and maybe 2, 8, 14. So let's imagine this one as a height, and then this one is weight. Okay, and then this guy is really highly correlated one. I mean exactly correlated one, linearly dependent one, right? And so A transpose A, let's see, compute that. 같이 건드리네. Okay. One, 4, 7, 2, 8, 14. 너무 큰 걸 썼나요? 66? 처음 건 어떻게 했는데 오케이 여기 2배다라는 걸 이용해서 이거랑 이거 내적하면 이게 2배니까 66이 2배가 되겠죠? 132 네, 여기도 132 여기는 네요. 네. 66에 4배? 다로 쓸게요. 아, 이건 이제 40, 그러네요. 45도를 모이는 건 말이 안 되는 것 같고, 지금 이 상황에서는 지금 얘랑 얘가 이제 시메트릭함과 동시에 같은 방향으로 되어 있죠. 근데 그 방향은 45도는 잘못된 설명이네요, 내가. 왜 아까는 그렇게 안 됐지? 여기 하나 더 하면 32, 21. 이쪽은 66에 3승. 그쵸? 66에 몇이 되죠? 여기 66에 3승, 66에 6승, 66에 36승 아닌가? 3, 9승? 그죠? 9승. 그렇죠. 그럼 이것도 시메트릭함과 동시에 네. 이게 내가 같은 거라고 그러니까 네네 그렇죠. 이게 지금 같은 방향을 나타내는 벡터들이 스케일은 다를 수가 있는 걸 내가 간과를 했네요. 그죠? 그래서 이거는 이제 같은 벡터지만 이 첫 번째 두 개, 두 번째 벡터가 같은 방향이라고 해서 요 두 개 숫자가 똑같아야 될이라는 가정은 필요는 없죠. 왜냐면 두 번째 벡터가 같은 방향을 가리키되 이제 스케일러 멀티플로서 훨씬 긴 벡터가 되면 되니까요. 그러면 여기서도 지금 완벽히 지금 linearly dependent한 벡터가 나오잖아요. 그래서 이제 여기서 이제 얘네들이 이제 linearly dependent하다라고 하면 여기서도 거의 그렇게 나와요. 여기서 이건 완전히 linearly dependent한 경우고 약간 틀어지는 경우. 그러니까 뭐 이거 한 7.9, 14.2, 여기도 뭐 한 3.3, 11.7, 뭐 20.5 이렇게 되면 이게 거의 highly correlated 되는 어떤 세 개의 variable인 거고 이 경우에도 이제 그 A transpose A를 해보면 뭐 당연히 이제 linearly independent 벡터가 나오긴 하지만 아까 얘기했던 것처럼 세 개의 그 어떤 벡터의 방향이 거의 이제 유사하게 돼요. 그래서 이제 아까 그런 문제가 생기고 regularization은 그걸 이제 쫙쫙 각도를 쫙쫙 펴준다. 약간 이런 측면이 좀 있어요. Any other questions? 네.
A 트랜스포즈 A가 공분사라고 볼 수 있잖아요.
네, 뭔가 그램 매트릭스 같은 역할. 그램 매트릭스가 아니죠. AA 트랜스포즈가 그램 매트릭스고. 네, 뭐 하여튼 네.
거기다가 이제 람다를 더해주면
네.
공분사를 표현하는 기저들을 축을 약간 배양시킨다고 보면 그게 뭐여질까요?
네, 뭐 그렇게 볼 수 있어요. 그러니까 이게 이거를 공분사 매트릭스에다가 램다 i를 더한다는 거는 셀프 베리언스, 그러니까 자기 자신과의 베리언스를 굉장히 키워주고 상대적으로 그 코베리언스, 그러니까 서로 다른 베리어블 간의 베리언스, 그게 코베리언스잖아요. 그 코릴레이션 혹은 그 코베리언스는 굉장히 상대적으로 작게 만들어준다는 뜻이잖아요. 그러니까 그 말은 뭐냐면 그 여러 베리어블들을 statistically independent하게 만들어준다는 얘기가 되죠. 왜냐하면 공분산이 거의 상대적으로 0에 가까워지는 거니까. 이게 뭐 정확한 그 얘기는 아닐 수 있지만 어쨌건 상대적으로 각자 자기 자신들에 대한 베리언스가 이제 다른 애랑 가지는 어떤 코베리언스보다 훨씬 크면 이게 곧 statistically independent한 케이스로 점점 가까워지는 거니까 뭐 그런 측면에서는 뭐 네, 또 다른 질문 있어요? Right, and then can we do this kind of same trick for L1 norm, L1 regularization case as well? So I'm not entirely sure, but I think I remember it is also possible up to, I mean, for one norm cases as well. So ax minus b, 2 norm plus now x1 norm, right? In this case, yeah, let's do the same trick. So we have a matrix A and then x minus b, right? And then 1 norm, right? And then 이건 안 되나? Okay, so I think we can just apply some simple trick of changing it as something like this, right? So this one norm of this vector x1, x2, x3 is represented as this two norm, right? Then we have a lambda, lambda gets inside over here because lambda is assumed to be the positive number. And then we can do the same trick, right? Yeah, well, I'm not sure, yeah. It may not be possible because here we have absolute value of an x1 through x3, but here we have x1, x2, x3. So they are not the same, okay? So here, how we were able to change it into this form was because this x part was the same between these two, right? But here, in this case, yeah, we need this square root of an absolute value of an x1 and x2 and x3. So this one is clearly not the same as this guy. So yeah, we may not be able to obtain the closed form solution in this case. So I think I was wrong. Okay, so and so this kind of regularization is also quite useful for mainly for the numerical stability that I discussed. So in some cases we may have some underdetermined system. So yeah, I don't even know the details about it, but I once published my very first paper in 2007 or 8. It was about the microarray data from the bioinformatics area, and then microarray data, due to some reason, collecting one sample of this microarray data is so expensive. So suppose it costs maybe several thousands dollars, for example, and then it is really expensive to obtain one single sample. But from that experiment or measurement, we obtain really large number of features or input variables. Okay, so in this case, our linear system is really underdetermined system. So we have so many variables. I may have drawn too much, but we may have maybe 3 of the samples. So in this case, so we have many variables as well, and then something like this. So we still perform this linear regression based on this least squares optimization problem. Okay, so in this case, we have matrix A, and then what is the A transpose A? So we have this matrix, and so it's something like this. Okay, so it's a really large matrix corresponding to A transpose A, right? So it is basically, it is certainly linearly dependent, right? It is linearly dependent because we only have maybe 3 columns, right? And then we have to create many of these columns. So using the 3 columns, we create more than 3 columns by using the linear combination coefficient. So for the first set of these 3 values is forming the linear combination for the first vector, right? So you guys know that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then it is 1, -1, 2, and then 1 times this guy, and -1 times this guy, 2 times this guy, and then that will form this guy, right? And so we have many different column vectors formed as a linear combination of only the 3 vectors, right? So clearly this matrix is a rank deficient. In other words, so this is having a linearly dependent column. Okay, so in this case, our linear system, I mean, this guy doesn't have an inverse matrix, so we cannot even apply the normal equation as a closed form solution because it doesn't have an inverse matrix, right? But here, our regularization is a really useful remedy for it, because in this case, if we add a small value onto it, okay, and then at least this kind of adding the regularization term or regularization parameter values along the each of our diagonal elements, and then it will be guaranteed to make this matrix having a linearly independent column, and thus it will have inverse matrix. Okay, so when I did my PhD, my advisor was really specialized. I mean, she was an expert in linear algebra and numerical analysis, and her main research area was least squares problem. And so, and there are several interesting constrained least squares problem where, for example, the topic that I worked heavily on was called non-negative matrix factorization, and that is basically imposing additional constraint that our linear regression coefficient should be non-negative 1. Okay, so they cannot be -1. Okay, so in that case, it will help us. It will give us some additional interpretability because our model is only adding the 3 features. Okay, so sometimes subtraction becomes tricky when interpreting the coefficient corresponding to that variable. And so so we will see some method called non-negative matrix factorization as part of our class because I plan to explain it in detail. But anyways, so given this linear system or least squares, we have constraint that every element of vector x is non-negative. Okay, in this case, we can consider this constrained version of least squares problem. And anyways, from that problem, this normal equation, and then solving this normal equation is the key part for this task. And so typically in that algorithm, whether this matrix is a invertible or not, by default, just for the sake of a linear, numerical stability, by default, the algorithm is just adding a small number, small value along the diagonal to make this matrix is at least at least invertible. Okay, so that we have no problem in continuing to solve as a normal equation. So that way, we use this as a kind of some heuristic to make our algorithm work stably. Any questions so far? Okay, then let's take a break for 10 minutes and resume at 5 p.m.
비슷한데 양가니까 레귤라이제이션 이렇게 더해져서
네.
이렇게 주고
this term is making this function nonlinear with respect to y, right? So there's no way that there's a closed loop solution. I
okay.
think that's the analysis.
Yeah,
It
that's
explores
yeah.
these limits.
Okay. Yeah, I think that's a really good explanation for justification. Thanks.
말씀하신 부분은
네.
L2는
네.
그 인풋 피처에 대한 코에피션트로서의 웨이트 그
네.
파라미터를 컨스트레이션하는 거고 레귤러라이제이션.
네, 좀 변형을 해주는 거죠.
근데 요새 리걸렉 관련 논문을 보면
네.
간간히 그 오소고날 레귤러라이제이션이라고 해가지고
네.
그 W W에
네.
대해서
네.
그 아이덴티티 빼주는 그런 게 있더라고요.
네.
의미적으로는 왠지 웨이스를
네.
오서거널리티하게 해서 뭔가 유용한 정보를 빼내게끔
네.
학습시켜주는 거 같아요.
네네네. 그거는 지금 여기서 다루는 거랑 약간 다른데 그건 이제 리니어 트랜스포메이션. 그러니까 저희는 방정식 혹은 이런 리스퀘어로 어떤 주어진 뭐 이렇게 돼 있을 때 그 x를 풀고 이러는 걸 하는데 이제 그 리니어 트랜스포메이션에서는 일단 어떤 arbitrary한 어떤 인풋 벡터 그게 이제 그 특정 레이어에 이제 입력으로 들어오는 어떤 그 노드 수만 인풋 레이어의 노드 수만큼의 하이 디멘셔널 벡터가 들어오면 그걸 이제 뭐 wx로 이제 나타내는 어떤 y 벡터를 구하는 거잖아요. 근데 그 w 벡터가 실제로 어떤 역할을 하냐면 이 프로젝션이라는 역할을 하거든요. 근데 그 프로젝션이 실제로 그러니까 그 프로젝션 방향이 그 wx라고 생각하면 그 w의 그 로우가 기본적으로 그 프로젝션을 시키는 어떤 축의 역할을 하거든요. 네, 왜냐하면 그 로우가 이제 주어진 인풋 피처랑 이게 저기 그 이너 프로덕이라는 거는 이너 프로덕은 이게 네, 가까이 길이가 있긴 하지만 이 코사인 세타라는 내적은 이제 두 개의 길이 곱하기 코사인 세타니까 코사인 세타라는 이 요소가 이제 약간 프로젝션을 해요 이 축으로. 그런데 이제 중요한 게 이제 이거를 W에서 이 로우들이 다 비슷한 방향을 가리키고 있으면 우리가 이 어떤 주어진 어떤 정해진 하나의 어떤 피처 포인트를 어떤 인풋 피처라는 그 벡터를 비슷한 방향으로 프로젝션을 한다는 얘기가 되거든요. 그러면 그게 이제 비슷한 성격의 축을 뽑아낸다는 뜻이에요. 그러니까 그게 무슨 말이냐면 이제 저희가 키 몸무게가 있으면 저희가 뭐 어파인 트랜스포메이션 측면에서 뭐 예를 들면 몸무게 빼기 키 플러스 100. 그러면 이제 뭐 키가 몸무게가 70이고 키가 170이고 그러면 이제 딱 그거를 하면은 0이 나와서 이거는 이제 과체중의 정도가 0인 거고요. 그러면 이제 키 빼기 몸무게 빼기 키 플러스 100이라고 하는 요소가 어떤 주어진 키와 몸무게라는 피처에 대해서의 어떤 그 특정한 피처를 뽑아내고 있는 거고요. 그 피처를 뽑아내는 방향은 그게 곧 뭐냐 하면 그 키에다가는 마이너스 1, 몸무게에다가는 1을 곱한 그런 어떤 방향으로 프로젝션을 시키고 있는 거거든요. 네. 그렇게 되면 그게 이제 또 비슷한 방향으로 예를 들면 뭐 1.1 곱하기 키 마이너스 0.9 곱하기 1.1 곱하기 몸무게 빼기 0.9 곱하기 키 플러스 100 뭐 이런 피처가 또 하나 또 다른 축이 W의 두 번째 로우가 그랬으면 사실 그 두 개는 사실 같은 거의 비슷한 방향으로 프로젝션을 하고 있는 거기 때문에 거의 비슷한 시멘틱한 의미를 뽑아내고 있는 거라고 볼 수가 있고 이런 이제 중복성을 막고자 하는 것이 그 이제 올소모널리티 컨스트레인트의 좀 요소가 돼요. 그래서 이 한 축으로 일단은 프로젝션 시켜갖고 이쪽 성분을 우리가 뽑았으면 이쪽 성분은 우리가 전혀 뽑지 말고 이거랑 이제 수직인 성분으로 이제 나머지 프로젝션 그 디렉션을 우리가 세팅을 하면 이 첫 번째 축에서 뽑아진 그 성분이 중복이 되어져서 이쪽에 들어가지 않을 거라는 거죠.
의미적으로 보면 좋은 것 같은데
의미적으로는 좋을 수 있는데
다 쓰진 않아요.
의미적으로는 좋을 수 있지만 그게 그러면 성능엔 좋으냐? 그렇지 않을 수도 있거든요. 그러니까 무슨 말이냐면 그게 실제로 과체중의 정도라는 게 의미상으로는 중복이 돼도 우리의 뒤쪽에서의 그 뭔가 실제로 뭐 어떤 당뇨병을 클래시피케이션 하거나 이럴 때는 이게 약간은 이 축으로 뽑아야 될 수도 있고 저 축으로 뽑아야 될 수도 있고 그러니까 여기에 굉장히 이제 우리가 뽑아야 되는 그 정보들이 밀집되어져 있을 수가 있고 그러면 사실 이쪽으로 어떤 한 축을 뽑았다고 해서 그 축에서 뽑혀진 정보랑 오버랩이 전혀 없는 상태로 나머지 정보를 뽑는 것이 그렇게까지 또 좋지 않은 전략일 수 있는 거여서 사실 뉴런 넷이 그냥 가만히 내버려 두면 그게 이제 올소원하라기엔 당연히 안 나와요. 그러니까 이제 그 방향은 당연히 어느 정도는 또 각도가 또 비슷한 어떤 그런 축들이 혹은 그 로우들이 W 매트릭스에 존재할 거고 이제 그런 애들은 뭐 뉴런넷이 또 그만큼의 그러니까 오버랩이 굉장히 많은 어떤 피처를 두 개의 디멘전 간에 정보의 오버랩이 굉장히 많은 형태의 정보를 뽑고 있다는 그게 어찌됐건 클래시피케이션에 도움이 되기 때문에 그렇게 뽑고 있다는 거라서요.
그것까지 알아서 해주는.
네, 그렇죠.
네.
근데 올소거널러티는 아마 이게 조금은 좀 해석의 용도로도 또 해석이 좀 좋아지고요. 뭐 좀 그런 측면이 좀 있어서 네, 하여튼 그런 게 조금 뭐 있습니다. 네.
혹시
네.
굉장히 설명해 드릴게요.
네.
여기서 리노멀라이제이션 7이 되면 이제 그냥 매트릭스에다가 IN 더하는 방식을 그
네.
뉴머리컬하게 인스테빌리티 줄이기 위해서
네.
그걸 다른
네.
방식으로 매트릭스 바꿔 나가는 거랑
네.
오늘 수업 내용이랑 어느 정도 연관성이 있는
뭐 비슷할 수 있어요. 네. 비슷할 수 있어요.
람다가 대신 힐러 바뀌고 좀 매트릭스의 변형이 있을 뿐이지.
네, 맞아요. 네. 이거는 일단은 우리가 람다라는 어떤 값들을 우리의 오리지널 피처 스페이스에서 이렇게 더할 수도 있고, 저거는 뭐 약간 좀 또 식을 얼핏 보면 뭔가 이렇게 변형된, 그러니까 이제 우리가 뭐 아이겐 디커머션하고 화이트닝을 한다거나, 그러니까 PCA를 통해서 화이트닝을 하면은 이제 뭐 그 코베리언스가 동글동글한 유닛 스피어로 딱 나타나는 그 뭐 그런 식으로 이제 피처 거기다가 가서 이제 어떤 그 아까 이야기했던 람다 i를 더할 수도 있고요. 이게 오리지널 스페이스에다 그걸 더하느냐, 뭐 저쪽 가서 더하느냐, 약간 뭐 이런 좀 초이스가 좀 차이가 있는 거죠.
그리고 저희 혹시 있는 건
그렇죠. 그거 있다고 했죠 아마.
네, 저희가 시작하려고 했는데
아,
이게
네.
실상 있는 건지 없는지
네, 알았어요. 그거 내가 다시 그거 해갖고 공지를 할게요. 네.
미네랄 나였거든요. 되게 미네랄 뭐 유턴하면 마법을 들어가지고 미네랄 보다 그 이렇게 써서 이게서 놀라 있는 건데 우리가
무결이 좀 어두운지 않는데 거부가 아니고 스킬이다. 그래서 그런 거지. 맞아. 그 조지병식 대신.
설명이 그러면은 70% 이상 열리죠. 70%까지는 좀 안 될 것 같긴 한데 일단 경필 재성 학생을 좀 넣으셔도 돼요.
네. 몇 프로가 나올까요?
40%? 40%? 네.
이거 지금 그게 조건이 이제 아니야 이거 일정 숫자가 그런데 그래도 몇 명의 조회 시간이 그래야 광고가 들어가겠지.
Right, let's continue. Okay, so if we just, even before considering this ridge regression version or L2 regularized version of least squares, if we just add just a small values along the diagonals of our A transpose A, and then it will allow us not to worry about any kind of potential stability, numerical stability issue being due to this linear dependence or bad condition number of our A transpose A. Okay, then okay, so in the case of L1 regularization, it is called a lasso. Okay, and then it has an interesting property of suppressing, in terms of the patterns, to suppress our coefficients. So in this case, it has the effect of making some variables, some coefficient, completely zero. Okay, so here in this case, if we increase the regularization parameters more and more for the L2 regularization, all the variables, even though they are strongly suppressed towards zero, but they are not exactly zero. But in the case of L1 regularization, it is giving us, at this point, for example, when using this lambda value as a hyperparameter for the L1 regularization term, and then we can, okay, let me move it to over here. And then we can see that this black line has been completely becoming zero. Okay, so in this case, at some point, those values, those parameters or coefficients, will start to become exactly zero at some point. Okay, so that is the effect of that is one benefit of using L1 regularized least squares, because in this case we can, if we find some completely zero coefficient, and then it means that we can completely ignore or exclude that variable from the beginning in our model, right? So if we started from the 10 different variables, what's the main idea of this shrinkage method compared to this stepwise or variable selection? So in this case, we use a strictly subset of input variables. So out of 10 variables, we may use only 7 of them, right? But in the case of this shrinkage method, we basically use all of them, but suppress all the variables with some force, right? Some amount of force, right? And so, in this case, in the typical, L2 regularization, none of them becomes zero, okay? Although they get closer to zero. But in the case of L1 regularization, so some of them is completely becoming zero. So that is the beauty of L1 regularized least squares, because we can, it has really the effect of variable selection, because we can exclude out those variables that have the zero coefficient. And let me give the intuition of why this L1 regularization gives us exactly zero value for our linear system or linear regression model. So suppose we have ax1 plus bx2 plus, for example, c. So this is a weight and height, and maybe it's a lifespan. Okay. So in this example, yeah. So we will have some training examples and their training loss over here, and then plus a squared and b squared. And here, do we impose the regularization on the unbiased or not?
No.
No. It is a probably good exercise or exam question for the Andrew's machine learning course, but we don't do the we don't impose the regularization on the unbiased part. Okay. I'm gonna skip the reason, but yeah, this is our regularization and the lambda. Okay. So in this case, suppose currently a is 3 and b is -2, -2, and then in this case, so we will have some gradient signal or gradient value, partial gradient with respect to a. Okay. And then from here, yeah, the gradient with respect to a is 2 lambda a, right? And so here, if a is 3, then let me just use it as 0.1. Okay, and then in this case, 2 times 0.1 times 3, because the current value of an a is 3, so it is 0.6, right? And so we are imposing the gradient descent, right? So we have a step size of maybe 0.3 as our step size, and then 0.6, right? So currently a is over here, right? So this is current value, and then when considering this as a kind of additional force, as a gradient, and then that force is pointing towards the origin, right? But what if b is -2? The negative value is the -2 over here. So this is our b, and in this case, the partial gradient coming from the regularization term is 2 lambda b, and so it is 2 times 0.1 times -2, and so -0.4. Okay, so we are performing the gradient descent, and so something like this one. So -2 plus 0.12. So gradient direction is also pointing towards the origin, right? So if we view this as an additional force, the source of an additional force in the middle of our gradient descent process, and then we are imposing this force towards the m0, right? And then how about what if our value of our parameter, instead of 3, suppose our value was maybe 4, which is really already close to origin, right? And then accordingly, this gradient term is proportional to our current value of a variable, right? And so our gradient coming from 2 lambda a becomes also quite small, right? So in this case, even if we had a really large force, but here we will have a really small force towards 0, right? So when our variables are around 0, and then accordingly our force will be diminished or will decrease, right? So that's why we obtain not exactly 0 coefficient, right? Because as they get closer to 0, and then the force is coming from this regularization term of L2 regularization will be also small accordingly, right? But the scenario becomes different when considering L1 regularization. So in this case, L1 regularization, we have some training loss, and then lambda times A, lambda times B, right? So what about the gradient over here? So gradient with respect to A is lambda times 1 if A is positive, or non-negative, or A is negative, and then lambda times negative 1, right? So in this case, suppose, similar to the previous case, we have an origin over here. Suppose A is currently 3, right? And then lambda is 0.1, and then lambda times 1. And then we are considering the gradient descent, right? And so the force will also exert it towards 0, right? And then what about the negative 2 case? So in this case, I mean, it has the same gradient, right? In the place of B, right? And so in this case, the same amount of gradient or same amount of force will be exerted over here, right? And this force, the amount of force, will be actually the same even when we have really small value close to 0, right? So from here, we also have the same length as this guy and this guy, right? So the direction will change in terms of the force, right? But so that direction is always pointing towards the origin, right? But the amount of force will remain the same. And so regardless of whether the variables are really far from the origin or really close to origin, the force will remain the same. I mean, the amount of force will remain the same, and that way this guy will just become 0 easily, right? So that way we obtain this kind of sparse kind of solution, or some coefficient to be completely 0. Any questions? 네.
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 L2 할 때는 0이 왜 정확히 안 되는지를 이해를 못했거든요.
네. 그러니까 이 0에 가까워지면 가까워질수록 이게 힘도 작아진다는 거죠. 왜냐하면 2차식을 미분하면 1차식이 나오잖아요. 그래서 이제 2램다 A, 2램다 B가 나왔고, 그러면 이제 A 값들이 혹은 B 값들이 이제 0에 근접해지면 질수록 이 힘도 굉장히 작아지기 때문에 0에 거의 근접했다? 그러면 거의 0으로 잡아 당기는 힘이 없어지는 거예요. 그러니까 이제 정확하게 0으로는 못 가는 거고요. 힘이 다해서. 여기서는 그렇지 않고 힘이 딱 고정된 정도로의 힘이 발생이 되고 있기 때문에 0에 가까워졌다 하더라도 뭐 멀었을 때나 가까웠을 때나 이제 동일한 양의 동일한 크기의 힘이 발생이 되기 때문에 딱 얘를 0으로 확 붙여준다는 거죠. 이게 약간 컨셉추얼한 설명이긴 하지만 뭐 그렇습니다. 또 다른 질문. Okay, and also because we discussed some non-trivial amount of a probabilistic perspective. So even though I'm not going to give a full proof, but this solution for ridge regression and the lasso can also be viewed as a Bayesian approach. Okay, so in the case of Bayesian approach, we consider the generation order of our random variable, and also most importantly, our parameters or coefficients are now a random variable, right? So they are some random variable having some uncertainty based on some Gaussian distribution or any other distribution, right? And so we have those kind of prior, which is our starting point, and then we assume that these parameters are sampled from these prior distributions, right? And then applying our data, okay, and then maximizing the likelihood of our data, and then we obtain the posterior distribution of our parameters A and B, right? So we can interpret, or we can kind of analyze or derive the solution for our linear regression solution based on this Bayesian perspective, okay? And more specifically, if we start from the Gaussian prior, okay, Gaussian prior with the 0 mean, okay. So at first, I mean initially, our prejudice or our initial belief is that for each of our, let's ignore this part, and for each of our random variable which works as a parameter, as an A and B are having the Gaussian distribution centers at this zero mean. Okay. In this case, what's the meaning of it? Our initial belief is that A is the parameter assigned to this input variable x1, whether it is a height or weight or something like that. Okay, a particular input variable. And then our belief, our belief before looking at the actual data items, and then our initial belief is that, okay, our y or the target variable is not relevant at all with the input variable, this particular input variable. And then in that case, our belief is that the coefficient for this a should be 0 by default, right? So that belief is reflected in this zero-centered Gaussian. Okay, so if we use non-zero Gaussian with the non-zero mean, so it's kind of doesn't make sense, right? Because even before looking at our actual observation data, and then we have some kind of initial belief or prejudice that the y is positively correlated with our particular input value or input feature x. Okay, so like our lifespan is positively correlated with some weight or some height. Okay, sometimes such a belief may make sense, but sometimes it may not make sense, right? So our what would be our general kind of strategy? I mean, generally kind of reasonable strategy. That strategy will be to have a to assume that this particular input variable is not relevant at all to the target variable, and thus that initial belief has the high probability centered at 0, right? And then this Gaussian distribution, okay? And then once we do the linear regression based on this some kind of probabilistic setting, and then deriving or constructing our maximum likelihood estimate, and then we will have so the Gaussian, and then we will have once A and B are sampled or generated from their own prior distribution, and then this y is also assumed to be a random variable. Okay, but here x is fixed, and x1 and x2 are assumed to be kind of a fixed one, and A and B are already sampled as fixed value. And then how can we make this guy as a random variable? And then that random variable is by introducing some epsilon as a kind of an error value occurring in a particular observation or example where this epsilon is following the Gaussian distribution also with the zero mean and some variance. Okay, so in this case, so y is conditioned. I mean, P of y and A and B is also a Gaussian. And then what is the mean? So epsilon plus this value. So this guy works as a mean, okay, for this Gaussian. And then this sigma squared will be is variance as well. Okay, so that way we can consider this y as also a Gaussian distribution by assuming that this epsilon is a Gaussian one. And then once you obtain or derive the posterior distribution, and then that posterior distribution turns out to be also Gaussian. So starting with the Gaussian prior for A and B, and then epsilon is assumed to be Gaussian as well, and then based on this posterior distribution, and then this A and B and their posterior distribution will also remain as Gaussian distribution, but their parameters will change. Okay, so the parameter over here, the prior distribution initially had the zero mean and the unit variance as a parameter for initial prior distribution, right? But once we compute the posterior by reflecting our observation or training data, and then it will still remain as Gaussian distribution, but their mean will be shifted, and the variance will also be converted into another value. Okay, and so in that case, if we So if you guys remember, and then if you guys remember, once we obtain the posterior distribution, how can we choose a single particular or optimal value of A from this uncertain distribution? Okay, so there were several different strategies. The first one was to pick up the highest possible one, right? Argmax one, right? The highest peak of our posterior distribution. So that was called what? Mean? 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 So that was called a MAP, maximum a posteriori. Okay, so suppose our posterior distribution for A, which is our parameter, is something like this. Okay, so it is not even a Gaussian distribution. I'm just giving you some random or arbitrary distribution as a continuous random variable. Okay, in this case, so what will be the strategy to choose the optimal or single particular value out of this uncertain distribution? So in this case, this posterior distribution is saying that our parameter A can have the values ranging from negative infinity to positive infinity, but their probability are different, right? And so here, if we want to choose a single best one, and then our strategy, I mean, one possible strategy would be to choose the one with the maximum probability. Okay, so that is called, this is called a mode, right? 이거 뭐라 그러죠? 모듈?
최빈값.
최빈값? 네, 최빈값이 그러니까 이 값을 가장 많이 관찰을 할 거다라는 거죠, 확률적으로. 그래서 이 최빈값, 이거 모드라고 부르죠. Okay, so in this case, we can choose this guy corresponding to our mode, and that is called maximum a posteriori. Okay, so it's simply choosing the argmax, applying the argmax of our posterior distribution, right? So that is called a map. Okay, and another equally reasonable strategy would be to taking the mean or taking the average with respect to this probability distribution. So in this case, more exactly, it's A, and given our data, x and y, okay, so we can represent P of A given x and y as a posterior distribution of parameter A after observing x comma y as a kind of observed samples. Okay, so in this case, what's the meaning of this? So given this distribution, what is the expectation of A? Expectation of A over here. So intuitively, that expectation has the same meaning as like. So suppose this guy is our expectation, the average value, and then it means that we just split them into two parts of this guy and this guy. So these two.
Is it the average or the median? The median value?
Yeah, it's the median, right? So what is this guy? What's the interpretation of this? So I was confused. I was clearly wrong. But what's the interpretation of this? Was there no interpretation? When equating or when making the two sides of a probability the same as each other, and then that is called our median, right? So choosing the median is another possible strategy, but I would say the most general strategy or widely used strategy is to compute its expectation value. Okay, the mean. Okay, and then I thought it also has some geometric interpretation or intuitive understanding about it. I forgot it. So yeah. But anyways, you guys at least understand the mean based on this particular distribution, right? So if we compute that kind of mean of this distribution, and then I don't even remember the name of this method, but taking the mean with respect to this posterior distribution is the most widely used strategy. And when taking that strategy and then obtaining the solution, I mean the single value of A from this posterior distribution, okay? So that solution is actually, interestingly, that solution is coinciding with, I mean that is actually the same as the solution for this guy, okay, this ridge regression version, okay. And then where is this lambda coming from? Okay, the lambda comes from, I forgot the full details, but in terms of our prior, we can, we assume, we typically start with the zero mean all the time, but we have a choice of the variance, okay? So in terms of our prior, so suppose we have this kind of prior, and then its intuitive interpretation is that we have really strong belief or prejudice that our parameter will be simply 0, okay? So this strong initial belief will not change much even after looking at a lot of data that says A is non-zero value of maybe 3, okay? So in this case, our value is really remaining close to 0, right? But on the other hand, if we have this kind of thing, okay, in this case, we have really weak belief. Although the parameter will be 0 on average before looking at the data, but I don't preclude the situation that this value can be really large non-zero value, okay? So that is the interpretation of this prior distribution. But anyways, so we have a lambda over here, right? So we have the sigma over here that controls this strong strength of our prejudice, right? And so I forgot the detail, but if lambda squared gets large, and then our prejudice or our prior belief is weak, right? And then that means we will follow what the data says. We will follow more of the optimal point according to our data, right? And so that is corresponding to, like, so over here, so if lambda becomes 0, that becomes close to 0, and then it is equivalent to having the sigma over here as our prior distribution for A becomes large, okay? Weak prejudice or weak prior belief is corresponding to small regularization parameter, okay? And strong belief will correspond to small variance and thus large hyperparameter for the regularization, okay? And also you can see, you can, if you look at the probability and statistics book, and then you will easily see the full derivation about it, okay? So it will be a good exercise or a good experience to have to study this kind of thing in more detail. And also, what about this solution for lasso, okay? In the case of lasso, interestingly, ridge regression has the exact same form of the Bayesian approach, where we started with the Gaussian assumption or Gaussian prior. But this the lasso and the solution for the lasso regression is actually equivalent to the Bayesian approach, where we start with a different prior called Laplace prior, okay? Laplace distribution, okay? So Laplace distribution is something like this. So from here, let's ignore the green line because green line has a non-zero mean. Okay, so the other lines that have a zero mean, right? And then this also has this kind of a bell shape, or the distribution center that's zero with the unimodal shape. Okay, and in this case, it's certainly different from Gaussian, right? So it's like really sharp. It has a really sharp peak, right? But anyways, this can be used as another alternative for our prior belief for our parameters, right? So it's still centered at zero, right? And then away from zero, it will have a lower and lower probability, right? So it can work as a valid prior, right? And then now the question is whether, this guy can be used as a conjugate prior, which means our posterior distribution is also Laplace distribution. Okay, so we can set up such a setting. So in that case, Laplace distribution or prior Laplace prior is actually exactly corresponding to the lasso solution. And then let me give although it's a little bit vague explanation, but let me give just a little bit more intuition. So why is Gaussian distribution or Gaussian prior related to the ridge regression? It is because Gaussian prior will have x squared as the exponent of our Gaussian probability distribution. Okay. So oops, what is that? I need Wikipedia. So here you can see the squared term, right? So since we start with the zero mean, and so mu is zero, right? X squared is appearing over there, right? So that is somehow related to our L2 norm. Okay, and then now let's look at the Laplace distribution. Interestingly, it is almost having the same similar function form or expression, but over there it has a first order term of x, right? So that way it is related to the Laplace the L1 regularization. Okay. Okay, so although I didn't give a full detail, but if you are really interested, and then it will be a really good opportunity to study them in more detail. And you will, hopefully you will think of it as really interesting. Okay, interesting kind of connections between all the different perspectives. Okay, any questions so far? Okay, then. And then the last point in this chapter that I want to emphasize or point out is, although it's not involving the full detail, I'm not going to give you the full details, but it's just a little bit of an overview or some inaccurate insight or something like that, imperfect insight. But so this one is a typical regular L2 regularized least squares objective function, right? And so this is called corresponding to unconstrained optimization because we don't see any kind of constraint, right? So in the case of constrained optimization, we have, in addition to our objective function to either minimize or maximize, we also have some constraint to satisfy in the form of maybe some inequality or equality, right? So in the previous case of a non-negative matrix factorization, so I mentioned about additional constraint that our solution for beta beta should remain non-negative all the time, right? So that restricts the possible regions of our beta, right? So that is that is called a feasible set. So this is heavily related to convex optimization or optimization theory. So yeah, I'm not very good at it, but I just have a rough insight or overview about it. Like primal and dual stuff. So I'm already too old, so I may not find much time to study them, which is really unfortunate and sad. But because you guys are much younger than me, so yeah, you guys have much better chance or better environment to study or focus on these basic stuffs. Okay. But anyways, yeah. So that is related to like convex optimization or optimization theory, but yeah, this is clearly unconstrained optimization problem. But this unconstrained optimization problem can be converted into some constrained optimization problem where we have the original objective criteria, and then this guy is converted into some constraint. Okay, so here our objective criteria to minimize does not have this regularization term anymore, right? But instead we have additional constraint to satisfy, right? So it is a little bit slightly different perspective. So this guy is unconstrained optimization, and so all the values for our beta can be any values. I mean, as large as they can be, right? Although if they are large, and then they will be heavily penalized, right, due to this regularization term. But in this case of a constraint optimization problem, they cannot be as large as they can be, so they are bounded by some particular constant s over here, right? So in this case, all the possible beta should remain, should satisfy this equation. So roughly, this guy is like the circle. If we consider beta 1 and beta 2 as a two-dimensional parameters, and then this guy is circle. So our solution should be only found only within this region. Okay. And then now this guy can also be represented as a some kind of functions. Okay. So for example, suppose we have a single global optimum. So it is like you can think of some kind of goal over here, where this one is minimum possible or lowest possible point, and then it gets higher and higher, right? But our solution should only be found inside of the circle due to this this constraint, right? And so what will be our solution? It will be somewhere like this, okay, somewhere like this, which is the point that is lowest possible. I mean, right? The lowest possible, considering this original mountain. That mountain is this guy, right? So my point is that even though we didn't prove it, but this unconstrained optimization problem can be reformulated or rewritten as this constrained optimization problem. They have the equivalence relationship. So one can be converted into another, and then the other can be converted into the first one. But here, one tricky part is that, okay, who determines the S? Okay, who determines the S? So to fully define this constrained optimization problem, we need S, right? Pre-given S, right? S is not something that we can freely choose and things like that. So that is predetermined constant value, right? So this constant value is obtaining or computing this constant value while converting the first one into the second one is non-trivial. Okay, so S cannot be easily obtained. Okay, S is only obtained after you figure out what the optimal solution is. So that way, even though, yeah, theoretically, these two forms have an equivalence relationship, but we cannot easily convert the first one into the second one because we cannot easily determine the corresponding S that will make this equivalence. Right, and then the second one is also, can be viewed as this constraint optimization problem that maintains this equivalence. And then this guy, when considering this L1 norm, and then I'd better use this figure in the slide. Okay, so the feasible set of our solution is this guy, right? Because beta 1, beta 2 is less than or equal to S, where S, suppose S is maybe 1, okay? And then it corresponds to this diamond shape, right? And we have to consider only those points inside of this diamond, right? So in this case, let's consider this original mountain of this, this guy, okay? The original training loss, okay? So in this case, if the mountain shape is something like this, and then it's likely to coincide, I mean, the optimal solution will be likely to be found at the vertex of our, one of the vertices in our diamond shape, okay? So if we have a three-dimensional case where we have a 3 variable and 3 parameters to optimize, and then in the three-dimensional case, and then you can easily think of like the three-dimensional diamond, right? And then somewhere over here, some point we'll have the lowest possible training error, but we have to find out the solution inside of this internal regions of this diamond. And so if it gets extended, and then it will likely to meet at one of the vertex, right? And if it meets at this vertex, and then it means beta 1 should be 0, right? Okay, so at one of these vertex, we'll have some variables corresponding to 0. Any questions? Okay, so that's it for the second chapter. And now let's move to the third chapter called the clustering. So clustering is one representative example of unsupervised learning, although clustering is not the only unsupervised learning, right? So what are the other examples of unsupervised learning? So what are the other examples of unsupervised learning? So density estimation, and maybe again in that sense, and also dimension reduction, like principal component analysis. Those methods don't require any additional labels, right? And then still they do something, using some particular machine learning method, right?
But in the case of GAN, like, isn't the discriminator needs some data too, right?
Right.
So in that case, anyways, is considered unsupervised learning?
I think so, because we have a bunch of data as our training examples, and we don't have any additional labels, right? But still, those data are existing data, and so we kind of utilize such a fact as our label, because these are real data, right? So in that sense, it can be viewed as a kind of a supervised learning, but in a sense that these labels are not separately obtained from a specific purpose, right? These are not additional information apart from our data, right? So in that sense, it can be viewed as a supervised, unsupervised learning. So so in the case of deep learning, we anyways impose, or we will set up or build build up a particular loss function. So in that sense, we are supervising the last layer output. So in that case, most of the deep learning methods can be viewed as a supervised learning, but yeah, I'm not sure. So, for example, the autoencoder, is that a supervised learning or unsupervised learning? So it's a little bit tricky. So it is unsupervised learning. That they don't have any additional labels, right? But still, it can be viewed as a supervised learning as well, because we certainly have the ground truth value for each pixel of our decoder output, right? Which is the original pixel value at the corresponding position, right? So in that sense, it is following the supervised learning approach. So with one of my former students who wrote a really famous paper called Stargan. He kind of remembered that I once mentioned that this autoencoder. Oh, you said last time you said autoencoder is unsupervised learning, but now today you are saying it as a supervised learning. So which one is true? So it was an interesting kind of topic to discuss. But anyways, I was also impressed that he remembers what I mentioned for a long time ago. Yep. Okay, so back to this clustering stuff. You guys know the general input and output setting of the clustering method, right? Okay, so there are a bunch of different interesting interesting applications of this clustering task. And so this one is my own example where I applied the clustering technique. So it's probably one of the second most cited paper that I wrote. The first most cited paper is Stargan, which is already over 200 citations, which was published last year only. But this guy was published in 2013. And then it got the second most citations from out of the entire set of my papers. But anyways, all right. So this is some example of a visual analytics research that integrates machine learning and machine learning or data mining techniques into some real-world data analysis applications. So here I performed the clustering on the set of given documents. So here in particular, I used review data. So I chose one particular TV product available in or sold in Amazon.com for a particular TV model, and then I just collected all the reviews about this TV. And then these will be just the textual data for each review article, and then apply the clustering. In particular, when applying the clustering into the document corpus, is sometimes called the topic modeling, although this topic modeling is focusing on the soft clustering method, right? But anyways, so when I apply the clustering method, and then each dot is representing a particular review article. So one review article is represented as a single dot, okay? And then they are colored with respect to their cluster index, okay? And then here, if you imagine the centroid of each cluster, similar to like a k-means, and then k-means will give us naturally the centroid, the coordinate, okay? And then among the coordinate, the coordinate corresponding to each dimensions, what is our each dimension of the textual vector representation? It will be, for example, bag of words, right? Each dimension is corresponding to a particular or distinct word defined in our dictionary. And then for a particular centroid, okay, centroid. So for example, let's consider the signs of the centroid vector. So if we consider the bag of words vector representation of our original documents, are there any negative value at all? No, right? So it is at at least 0 in case that particular term didn't appear at all, or if it appeared at least once, and then that corresponding value in that dimension will be positive one. Okay, so 0 or positive. So we can think of all these back-over vector representation and their corresponding points located in this, I don't know, I forgot the name of it, but it is all located in the first quadrant, something like that. So in the case of two-dimensional case, I mean the two-dimensional vector case, suppose we have only the two terms, maybe like and hate, okay? And then these are the two keywords forming our vocabulary, okay? And then every document will be placed over here, right? So there will be no document possibly placed over here because we cannot have negative values corresponding to each dimension, right? So it is called the first quadrant, or 일사분면이라고 하죠. So we can easily imagine this first quadrant in a much higher dimensional space, right? And then if we perform the k-means, okay, the centroid of our k-means will likely to be still, I mean, all of the centroid will also be remaining or staying in this first quadrant, right? So in that case, all the coordinate values of each centroid will be positive value, and then suppose our centroid is found over here, and then it will be something like 5, 1. Then what does that mean? If we think of it as a kind of virtual document, okay, the centroid is anyways one particular point existing in our feature space, right? And so we can interpret it as particular data item, right? So if we view this vector representation as our data item obtained from the back-of-words representation, and then it means this document has 5 occurrences of like and only 1 occurrences of hate, right? So in this manner we can make sense of the semantic meanings of each cluster when it comes to the back-of-words vector space. Okay, and then of course we will have many more dimensions, right? Each of which is corresponding to a particular keyword, right? And then obtaining the centroid of each cluster, and then which value is the largest one, and what is the corresponding dimension and its word, and then if we choose, maybe if we select top 3 keywords that has the largest value in that dimension, okay, and then we obtain this kind of summary for each cluster. So in this particular cluster, the centroid has the largest value corresponding to this keyword dimension, and the second largest value corresponding to this keyword dimension. And then it's giving us some interesting interpretation of our textual data. So so we have a bunch of dots corresponding to our review articles, and then here this one is another product of the Hyundai Genesis car, and then I collected the review articles from some websites, okay, and then for this cluster, it is composed of series and Zera and compare. So Zera is American name of a grandeur, and so we can kind of see that people often discuss or often compare this Genesis, which was a newly born car at that time, against the existing Zera car. Okay, so in the U.S. It is a little bit of a shame, but in the case of U.S., Hyundai is not considered as a luxurious brand. Okay, so Genesis was probably the first car that's positioned at a little bit of a luxurious market, but Hyundai couldn't set the high value or high price point of this car, so the price was relatively much cheaper than Korea, okay, than its value, and so there were not much of a difference in terms of cost or prices between the Genesis and the Azera. So people kind of consider these two cars at the same time. And then it is saying that okay, this car in black looks nice, and then maybe people are comparing this car against a Lexus as well. And this kind of thing is about the economic aspect of this car, right? And this car is about the tire used in this car, right? And at the same time, it seems that this car has some issues or problems in the gear shifting system. Okay, so that's how we can kind of get the summary of the large scale data or large scale textual corpus through this clustering method. And by the way, does anyone know why this economy and fuel seem to go well with each other, right? But why is GPU included here? And Dunlop navigation. GPS. Yeah, right. 근데 뭐라 그랬죠? GPU라고 했어요? 전혀 인지도 못했네요. 아, 치맥기가 있는 것 같아요. 뭔가 그런 얘기가 있던데 네이버 뉴스에 그거 아직 내가 킵해놓고 아직 보지 못했는데 뭐 약간 잠을 못 자면 언젠가 그 값을 치른다? 뭐 보상을 죄값을 치른다 약간 이런 기사가 있었고 치매의 주머니라고. 네, 어쨌건 Okay, so GPS. So why is GPS included in this cluster? Together with the economy and fuel and navigation and things like that. So I didn't pay much attention about this, but so at back then, about maybe 3 or 4 years ago, when I didn't do much of a research on the deep learning and this kind of text mining and also visual analytics was still one of my main research, and so I got many chances to present about my recent work at that time, and then I described this example a lot of times, and then I didn't pay much attention why these guys were included, but in a particular in a certain seminar, someone pointed out the issue, the subtle issue about why this was included here. Does anyone know? It's a really off topic, but let me explain in Korean briefly. 이게 뭐 약간 뭐라 그러더라, 이게 하여튼 연비를 제공해 이런 거 있잖아요. 연비 등급, 차 연비 등급 있고 막 그런 거 있거든요. 미국에 또 이렇게 뭐 연료 효율 등급 이런 걸로 해갖고 차 사러 가면은 차에 떡하니 그런 종이 하나씩 다 붙여져 있거든요. 근데 이게 뭐더라, 이게 뭐 하여튼 타이어인지 아니면 GPS 뭐 모듈인지를 뭐라 하여튼 어떻게 해갖고 이게 실제 연비가 이게 아니다 뭐 이렇게 해갖고 뭐 그런 이슈가 있었대요. 별로 전혀 중요한 얘기가 근데 뭐 중요한 거는 그런 것도 이제 일단은 이렇게 키워드만 보여주는 게 아니라 이게 하여튼 이게 좀 지금으로서는 굉장히 올드한 툴이긴 하지만 이때는 뭐 웹 베이스도 없고 이건 다 내가 자바 내가 나만 만든 건 아니고 하여튼 다른 또 콜라보레이터랑 같이 만들었지만 이제 자바로 열심히 만든 건데 스탠드얼론 툴로서 이제 하여튼 그래서 뭐 어쨌건 뭐 이게 지금 보면 동그라미도 내가 이쪽 구현하는 거 내가 죽는 줄 알았어. 진짜 죽는 줄 알았어. 컬러를 왼쪽 오른쪽으로 쓸지 내가 각도까지 다 센트로이드까지 맞춰가면서 이렇게도 실험을 해보고 이것도 다 학회 가서 진짜 밤새 코딩하면 진짜 뭔가 학회 가서 논문 쓰는 그 맛이 있죠. 내가 논문을 발표하러 학회를 왔는데 나는 여기에만 그치지 않고 내가 또 다른 논문을 나는 쓰느라 바쁘다.
스윙으로 저렇게 하시는
이거요? 네, 맞아요.
스윙.
네, 맞아요. 그래픽스 2D, 뭐 스윙, 뭐 다. 그래서 뭐 이런 거 다 뭐 이렇게 해갖고 다큐멘트도 다 확인할 수 있고 뭐 이런 거거든요. 어쨌건 Okay, so so I discussed a really off-topic one, but let's see. So in this case, yeah, in this particular research example or research piece, so in this case, it is basically the graphical representation of the centroid. When we click a particular cluster, and then this is really the coordinate of the cluster centroid in a decreasing order and its corresponding word dimensions. Okay, so here, so its example is like, so this is about the TV review data. So it had yeah, not surprisingly, the television as the top keyword in this particular cluster. But this television is almost a stop word, which doesn't have any meanings about this review data set about TV, right? So in this case, I removed this keyword in this centroid representation. So in this case, I just manually manipulated or controlled or changed the current centroid obtained by our clustering algorithm. Okay, and then I fixed that dimension, because if it is reverted back to the original value, and then there's no point of doing this manual interaction, right? So once the user interaction is performed, so I removed it, and then I instead boosted up or increased the weight of the recommended. So the two keywords is now becoming excellent product and also recommended, right? And then in this case, if I just fix that centroid artificially, and then in the subsequent like k-means iterations, you can think of it as a k-means, although I used non-negative matrix factorization as a kind of a soft clustering method or the topping modeling method. But anyways, once I fixed or manipulated this cluster centroid, and then I can see that, we can see that one data item got out of this pink cluster to another cluster, right? And so that is highlighted in pink. And so let's check the content of actual document. And so although it is really small, but it's the same with the, yeah, start with the do not buy this TV and so on, right? So that makes sense, because it is yeah, belonging to the cluster of DVD sound and problem. So here, what I did was to actually dynamically add one additional cluster in the middle of this entire iterative clustering step. So in this case, here the option is create new topic or new cluster from this particular document. So in this case, I fix or I add another cluster on the fly, and then set the centroid as the same as this particular document. Okay, and then now we will have additional cluster. So compared to the 5 clusters in total, we now have 6 clusters, and then the cluster in yellow in the middle is the newly created clusters, and then it has the keyword of a repair, problem, and turning, and all the documents are discussing the negative aspect, like do not buy this TV, and broken TV took 3 months to fix, and so on. Okay. So that's how we can perform this interactive clustering while making sense of or understanding our document corpus in an exploratory manner. So, so this work was kind of appreciated by the, especially the information visualization community, because it was considered as a kind of nice example of combining the user needs in the middle of the clustering-based analysis of our data, and we combine the user need, and then also we supported such a user need based on a newly created algorithm. So in order to add a new clusters on the fly in the middle of, for example, k-means, although I haven't used k-means, but yeah, NMF is much more complicated one. And so, how can we allow the algorithm to dynamically add additional clusters in the middle of this process? And then how can we allow our model to set a specific coordinates of a particular centroid? Okay? And then even, although I will not show it, but I also provided the new capabilities of dynamically merging the 2 clusters if they are similar to each other, and also if one cluster is a little bit ambiguous. Okay, and then I allowed users to split the single clusters into 2 or more to have a much clearer meanings for each separate clusters. Okay, so there is also another example of this clustering application. Any questions? Okay, and then also this clustering is also used in biomedical or bioinformatics literature. And there are many different clustering methods. Okay, but you may be familiar with already familiar with k-means clustering and also the hierarchical clustering. And if you remember, the initial input setting that we discussed over here. Yeah. So I remember I wrote something in this whiteboard. So that's why we don't have any handwritings over here. But roughly at a high level, there are two kinds of inputs describing our data for running any particular machine learning algorithm. The first one is the feature vector representation, and then the other one is graph or network data, right? So basically the network or graph data is indicating the similarity between any pair of data items, or dissimilarity, of course. Okay, so in the case of clustering, there are also two different types of clustering algorithm that basically that takes the input type of feature vector representation, or some other clustering algorithm that takes the similarity, pairwise similarity input. Okay. So especially when the clustering algorithm is taking the input as a pairwise similarity matrix, and then it is sometimes called the graph clustering. And also, I think I mentioned it already in the first lecture, but as is a specific application of this graph clustering, it's called the community detection. I think I mentioned it, right? Okay, so one of the professors in maybe SKKU or Seongyungan University, so she's working heavily on this community detection problem or task, and so her main task or problem setting is to be able to address like overlapping clusters. So in the case of clustering, we basically partition our data into multiple pieces where each particular data item belongs to one particular cluster, right? But what if we have this kind of overlapping communities or clusters? So those data items are belonging heavily to both of the two clusters. Okay, so in that case, algorithm should be developed in much more sophisticated manner, and so that is another kind of recent research trends or topics in this topic. Okay, so the graph clustering in this specific or representative example application is called the community detection, and also this graph clustering. I mean, one of the representative example of this graph clustering is called spectral clustering, that we will study as well. Spectral clustering. Okay, and also the spectral clustering is still a broad category containing many different specific clustering methods. Okay, so one representative method is called the normalized cut. Okay, so it is a she and Mali. I mean, this paper is so famous. I mean, it's gotten like maybe kind of VGGNet or AlexNet and that kind of paper. Okay, so it has that many citations. Why is it going to TE? Oh. right? So 15,000. Yeah, I'm just curious about VGGNet and its citation. I think it's less than several thousand, I think. Where is the paper? Oh, wow. It's already more than that. So, anyways, yeah, this normalized cut paper, yeah, was really seminal, advancement in computer vision domain, and the main application of this clustering algorithm called normalized cut, which is kind of spectral clustering, okay? And this normalized cut-based algorithm was successfully used in the, as you can see, image segmentation. But in this case of an image segmentation, if you're familiar with the semantic segmentation, it is a different one from this guy, because semantic segmentation is basically supervised one. For each pixel, we have a pre-given label, right, corresponding to a particular object, whether it is a sheep, dog, and cat, and so on. But in the when it comes to kind of general image segmentation, okay, and then we often do not assume any pre-given labels, but it's a semantic segmentation. It is a little bit difficult to find image segment. Okay. Right. Okay, this kind of thing. So, so we are given this a single image. Okay. So if you're familiar with the single SISR, does anyone know SISR? 네? 뭐라고요? 뭐라고요? 맞아요. So SISR is a single image super resolution. So that is the task of given just a single image, and then we want to increase the resolution of the original image into much higher one. Okay, so that is also addressed by the deep learning approach. But anyways, it is also single image based approach. So we are just given a single image, and that's the very first starting point to run the segmentation. There is no previous trainings or whatsoever. So we basically given a set of pixels within a single image, and then we perform the clustering on them. Okay, and then we may get this kind of clustering results. And so here we can see that those pixels are corresponding to this red or brown region is clustered into one single cluster, and then yellow one is clustered into the other cluster, right? So here, because this is not a supervised one, or this is not a semantic segmentation, as in its final output, we don't have any notion about, okay, this cluster is maybe building or church, and this cluster is maybe sky. There's no notion like that, because if we imagine doing the clustering, and then we just obtain the partitioning of our input data items, but we have no specific semantic meanings assigned for each cluster. So that's our job, right, to make sense of it, right? Okay, it looks like this cluster seems to be having this kind of semantic meanings and so on, right? And so this is also the clustering result in an unsupervised learning setting, and so it's just giving us the groups of our pixels out of this entire single image, right? And so this is called the image segmentation, and so the representative example of running this image segmentation in an unsupervised manner, and that is called, the most famous algorithm is called spectral clustering, and also normalized cut based algorithm. So the time's up. So that's it for today, and then let's continue with clustering stuff in the next Monday.
선생님 이거
참여학생 목록에 교수님도 포함되는데 하는데
나도
네.
포함이 되죠. 네.
저 잘 안 해가지고 혹시 주민등록번호 필요되는 거
아
있어요?
그래요?
네. 전화로
이거를 어떻게 하는 게 제일 빠를까요? 지금 내가 보내줄게요 바로
네.
메시지로.
교수님은 참여율 몇 프로로 할까요?
참여율이요?
네.
제일 적게 할 수 있는 만큼 제일 적게요. 10이나 15% 정도 될 텐데 그게 아마 미니멈이 있는데
네.
그 미니멈을 좀 물어보고요.
네.
그거를 좀 그 미니멈으로 좀 적용을 해줄래요?
네. 네.
잘못 쳤다. 이거 아니에요. 네, 다시 칠게요.
네.
네네.
I want to ask you about the exam. It's going to be on the 22nd.
Yes, right.
I just want to ask. On Monday I have two classes, so I have 3 exams. So I wanted to be sure. So normally, which kind of I know which kind of it's like really theoretical or it's more like
Kind
dealing
of,
with
yeah.
data. Or
Yeah, I mean, it will just a pen and pencil. I mean, pen and paper based exam.
okay.
So
And in class then, right?
yeah, right. And then it will require to just you to explain a particular concepts. Yeah, and also maybe some computations may be involved as well. Yeah.
Okay. So the other thing I wanted to ask you. I wanted in your YouTube videos, in the first class, there's 3 videos.
Right.
And they are numbered 1, 2, and 3.
Right.
And 2 is 1 and 1 is 2. So maybe you want to change that.
Oh, okay, I'll check.
In your first class. Okay. And the other
Yeah.
thing.
So sometimes, so I happen to pause and then I resume the recordings, and so that's why we may have multiple.
Yeah, and then they are just backwards in
Okay,
order.
I see. Yeah, that's good. Very good to know. Thanks. Yeah,
The other thing
I'll
is-
change the order.
I don't know. Okay, so I'm from 화공생명공학과. So I just started this semester and I wanted to ask you, my research is about the machine learning applied to kind of classification of molecules or prediction of molecular properties, physical properties. So since I started until now, I did like a classification of molecules through, the way of showing molecules by strings, there's many types of way of representing molecules. So I
Yeah.
pick one of those, I have a database. So my problem now is, let's say my database has around 10,000 molecules and I already classified everything and it does really well.
Yeah.
My problem is it's hard to get data that is kind of out of the normality. Like I want molecules that are really weird or not normal. So it kind of try to find different patterns. So my question is, do you think it will be worth a try?
Yeah, of course.
To create kind of data with kind of GAN kind of
I see. So you still are concerned. Yeah, your main purpose is to perform classification, but because you don't have enough data, so you want to apply GAN to generate the fake data to be used as an additional training data.
Yeah, so my worry is the data going to be really kind of similar to the spectrum I am giving as kind
Right,
of
yeah,
real?
yeah.
Maybe I'm
It's there is a kind of potential fundamental kind of potential issue, right? So we learn the generation model from the limited data,
Yeah,
right? So can we rely on this data as an additional source of data? So there is such a fundamental issue, but still this kind of approach is quite heavily attempted by recent researchers. Yeah. So I personally also work on similar kind of problems in some other domains. So it can be viewed as a kind of one-shot or few-shot learning kind of setting. Yeah. So because it only uses a limited amount of data, right? So I still see some great potentials, and I think that personally think of it as a kind of great research.
So it's worth of trying.
Yeah, of course.
Thank you.
Yeah. 네.
저희 시험 지원사 시험이 4월 말 2주 뒤로 알고 있는데.
네, 맞아요.
맞는 건가요?
네.
근데 아직 따로 이제 말씀 안 하시고.
네. 다음 주에 해야겠네요.
시험 진행하실
시험은 보려고요. 왜냐면 그래야
네.
좀 공부를 하니까.
네.
네.
알겠습니다.